Welcome everyone to another weekly ZX seminar. Today we have Alex Koziell-Pipe. We will talking to us about his paper towards faster quantum surface simulation using graph decompositions, GNNs, and reinforcement learning. Please, Alex, take it away.
Thank you, John. Okay, well, yeah, so as John described, I'm talking about this quite long title paper. The main idea is that we are using, that Richie, Yeung, and Matthew Sutcliffe and I are using ZX calculus, GNNs, which are graph neural networks, and reinforcement learning to improve quantum circuit simulation. But one thing one take home I want for this talk to be is that there is a bigger picture, which is that of combining ZX and AI to have some fruitful applications in the realm of quantum computing. Okay, so as an outline, classically simulating quantum circuits is actually quite useful, but in general, it's also pretty hard. And although it is hard for general circuits, there are some circuits that are actually easily simulable with classical computers. So one technique we might want to use is decompose a circuit into circuits that we can simulate efficiently. And we might want to do this to approximate a simulation, or we might have some circuits that are actually quite easy once we decompose them into these easily simulated circuits. This technique has actually been studied in the ZX calculus and improved upon for some quite efficient simulations. Those techniques that I just described are mostly heuristic or require domain expertise to actually perform. And in our work, we train a graph neural network using reinforcement learning to perform classical simulation via ZX calculus. And we find that our model actually improves upon the heuristic algorithm. And more generally, the ideas that we actually found in this work could be used for other ZX and AI applications. So to set the scene, why do we want to simulate quantum computations with classical computers? Well, at the moment, we're still in the NISQ era, where quantum computers are still limited by both the scarcity and the high error rate. And furthermore, in practice, it's not always clear whether quantum actually has surpassed classical limits. One good example is the 2019 Google experiment, where Google said, well, what we just did on a quantum computer takes 10,000 years on a classical computer. And then shortly afterwards, IBM came out with a rebuttal saying, well, actually, we just came up with a simulation technique that cuts that 10,000 years down to 2.5 days. And so it's quite important that it's not always clear at this stage where quantum computers are actually better than what we can do classically. And by pushing the limits of classical simulation, we can actually just raise the lower bound for that quantum advantage boundary. The other thing we can do at the moment, which is increasingly important in this NISQ era, is that we can test and debug quantum algorithms without having access to a quantum computer, which is somewhat difficult until we get, more accessible quantum computers. The other thing we might want to do is study error correction, where we can use classical simulation to actually decide and choose what noise we have and simulate specific errors that we want to study. Then, as I mentioned, we can benchmark practical quantum advantage. We can also simulate quantum hardware during development, and that saves us from having to actually build the hardware, which might be quite expensive, and we can produce we can model it using classical simulation, which doesn't require any actual physical building of the device. We can see just a pilot test whether it works or not. And then there are practical applications we might want to look at without that are also going to be quite costly to implement or inaccessible in the hardware we have available today. And that might be towards machine learning, finance, optimization, all those sorts of things. And with classical simulation, that makes it a lot easier to do for a lot of people who might not otherwise have access to this hardware. The problem is that classical simulation is pretty hard, and in general, it's sharp P hard. I don't know the technical definition off the top of my head, but sharp P hard is very, very hard. Like that's not going to be possible on classical computers. In practice, it's often easier. There are lots of cases where actually we're not pushing that upper bound of difficulty. And there's even a subclass of circuits, which are called stabilizer circuits, that we can simulate in polynomial time, which means that it basically means they're classically tractable. And there's the idea is that we might think, okay, well, given that there is this class of circuits we know how to simulate in a time that goes up with the square of the number of qubits, can we try and use this to make more general classical simulations faster? And indeed, let's just talk about stabilizer circuits. They're comprised of Clifford gates, which are CNOT, Hadamard, and phase gates. I've drawn in the ZX calculus here. These are efficiently classically simulated. However, they're not universal, which is sort of a good thing, because if we could simulate any quantum computation in polynomial time, then there'd be no quantum advantage. We can actually upgrade the stabilizer circuits to an approximately universal class of circuits for quantum computation. Approximately universal means that we can achieve any quantum computation to arbitrary accuracy. We can do this just by adding a T-spider or T-gate, and this is effectively where a ZX spider where the phase is a multiple of pi over 4. The T-gate itself is the pi over 4. Now, if we just look at Clifford plus T circuits, there are actually some ZX rules where we can remove T-spiders from a ZX diagram by expressing a T-spider as a linear combination of some stabilizer terms. What this means is that by performing this decomposition on all the T-spiders in a ZX diagram, we could reduce a Clifford plus T diagram into a linear combination of stabilizer terms, which we could simulate in polynomial time. So here's one decomposition. It takes one T-spider and it produces two stabilizer terms. And we can actually perform this on any multiple of pi over 4 as shown in the bottom diagram, just by unfusing a T-spider. Now, let's suppose we had a Clifford plus T diagram, we could apply this strategy of removing all the T-spiders using these decompositions, just iteratively applying this to random T-spiders in the term. And this would give us 2 to the power T stabilizer terms. And each of those would take n squared in the number of qubits time to classically simulate. So the total cost would go up with n squared, where n is the number of qubits, times 2 to the t, where t is the number of T-spiders. Now, that scales exponentially with the number of T-spiders, but it's pretty good if we have relatively low numbers of these T-gates. Here's the strategy I just described. And so we decompose into a linear combination of stabilizer terms, classically simulate them, and sum the results to compute a simulation of the original circuit. Now, each stabilizer term adds to the simulation cost. However, there are decompositions beyond the one I just mentioned where we get rid of more T-spiders at the cost of fewer stabilizer terms. This one, for example, gets rid of 2 T-spiders but produces the same number of terms. So if we naively applied the same strategy, we would get approximately 2 to the 0.5 n, or should be t here, stabilizer terms. So Okay, so we've got this metric of like decompositions, and each decomposition produces stabilizer terms. We kind of want to get the goal is we want to get rid of as many T phases as possible with as few stabilizer terms as possible. So to quantify that, let's talk about decomposition efficiency. So given that some decompositions remove more T phases using fewer terms, we're going to define this decomposition efficiency coefficient we call alpha. And that's just calculated, as you can see, where we take log 2 to the number of terms produced, stabilizer terms, and T is the number of T gates removed. Lower alpha means a more efficient decomposition. And so for the previous two, we can calculate that as alpha being 1 for the 1 T spider to 2 terms, and the alpha is 0.5 for the 2 T spiders to 2 terms. Now, there are actually even better decompositions, such as the magic 5 decomposition, as you can see here. What this does is this gets rid of 5 T spiders and produces 3 terms, which each have 1 T spider. So what we're doing is we're removing 4 T spiders to produce 3 terms, and we would hence define the alpha of this decomposition as approximately 0.396. One thing that will become important for the machine learning application is that if we want to apply this decomposition to a ZX diagram, we can choose any 5 spiders and unfuse pi over 4 phases. And that uniquely determines a magic 5 decomposition to apply to a ZX diagram. Now we've defined magic 5, but actually we can do even better. And there are these decompositions, as shown in the paper below, which are the cat decompositions. And these, in fact, can be applied to any spider of degree 3, 4, 5, or 6. And they have alpha efficiencies of 0.25, 0.264, 0.317, and 0.333, so even better than the ones we saw before. Another thing I would point out is that although they can't always be applied to a ZX diagram, they can be applied in the case that we have a spider of degree 3, 4, 5, or 6 using this unfusing process as we saw here. Another thing I should actually note that isn't on the bullet points is that the phase on the spider has to be a multiple of pi as well. So there are some limitations on where we can apply this. Whereas the previous decompositions, the magic 5 and the 1 or 2 T-spider decompositions can be applied pretty much anywhere as long as you have enough spiders. So we have this whole repertoire of decompositions. And as I mentioned, you can apply them in different places with some limitations. And we might think, okay, is it important which decompositions we apply and where when we perform this iterative process of decomposing each of these terms into a sum of stabilizer terms? And so, in fact, there is a state-of-the-art strategy by Kissinger, van der Wetering, and Vilmar, which apply a strategy of that chooses these decompositions in a specific order. So what they do first is they simplify the diagram using the full reduce optimization algorithm, and then they apply a single cat or magic 5 decomposition and the way that they prioritize them is in order of efficiency. So going back to the alphas we had before, the first thing they would try to apply is a cat 4 because that has 0.25 alpha. And then if they can't find one, they'll apply cat 6, 0.264, and then subsequently keep going until they find a decomposition that actually works. And so they will repeat this on all the terms until they have no cats. They have no cat states, which are these states that look like the left-hand side in this equation. And fewer than T spiders remain. So that's where we're left with diagrams where no cat or magic 5 decompositions can be applied. And then they just reduce these to stabilizer circuits using the 1 or 2 T-spider decompositions. And once they've done that, you can classically simulate the terms in polynomial time and compute their sum. And this strategy does pretty well. It gets quite a high efficiency. However, there are some limitations, which is that we have introduced something new in this strategy, which is that after each decomposition, this full reduce algorithm might actually remove additional T-spiders. And sometimes the choice of decomposition and where we apply it causes more cancellations during this full reduce process that removes more T-gates than you might have expected from just looking at the alpha coefficient. So what that means is that sometimes less of what we would expect to be less efficient decompositions actually result in fewer T-gates after full reduce. And so there's two things. There's the choice of decomposition, and there's also the location of decomposition that matter. And to really make these decisions optimal, you want to look at the broader context of the diagram. And the state-of-the-art algorithm doesn't do this. And if you did want to do this, at the moment, you would have to take this into account using manual inspection by ZX professionals, or I'm going to cheesily call Z experts.
Sorry, I have a question.
Of course, yeah.
So for the first bullet point, why you don't want to remove additional T-spiders?
This is actually we do want to remove additional T-spiders, but this is something that is this is an important point to make, because this strategy will prioritize decompositions based purely on these sort of equations you see here, where you see the decomposition, but you don't think about the broader diagram and how full reduce might affect the number of T-spiders you remove at the end. So the idea is, full reduce it's good that it removes additional T-spiders, but this algorithm doesn't necessarily take that into account implicitly when it's operating.
Thank you.
Okay, so that was actually a good place for a question, because we're going to change theme a bit and talk about the first ingredient of the AI-based strategy, which is reinforcement learning. And so this has already seen fruitful applications to things like professional games, such as the famous DeepMind's AlphaGo, the autonomous driving, robotics, and even large language models. So ChatGPT has a process where we use reinforcement learning to refine its ability to have conversations with humans. And the thing these have in common is that reinforcement learning typically is used where you have an AI agent, which we can think of as just an AI that can perform some sort of action. And this AI agent interacts with an environment. And so the key components really are summarized by this diagram we have here, where you have some kind of environment, you have some kind of agent that interacts with the environment, and the environment presents the agent with some sort of observation. The agent takes this observation and uses it to choose some kind of action it can take in the environment, based on some kind of goal that it's trying to achieve. And once it's performed this action, the environment will give the agent some sort of feedback, some sort of reward that tells the agent how well its action guided it towards its goal. And so in this way, the agent, by performing lots of actions in the environment, making observations and receiving rewards, tries to learn how to optimize for a specific goal, given the information it gets from the environment. Now, this kind of template allows us to reformulate this decomposition process as a reinforcement learning problem, where our observation from the environment is the diagram we want to decompose. The action is which decomposition we want to apply and where. And as reward, we're going to use what we call the effective alpha. So this isn't the immediate alpha you would get just from looking at the decomposition equation, but this says, how many terms do I have and what's the change in number of T-spiders after I actually perform the full reduce algorithm. So this reward takes into account the decomposition itself and the full reduce, and how well this decomposition performs, given that you're also doing this, you're integrating it into this full reduce process. And so what we're doing, yeah.
Can I just interject a question? And maybe this is a good question for the end, but you take the mean T count reduction. Is the mean the right metric? Don't you want to like maximize, like if a single diagram like cancels everything, that's like really, really good, right? So do you really want a mean here?
In what sense?
Like
Like the
suppose you have like a decomposition and you create 7 diagrams, and in 6 of those diagrams there's 0 cancellation, but in the 7th diagram it like completely cancels the whole circuit. You don't have to deal with it anymore. Is that like better or worse than if you have like in all 7 of them you reduce like by a little bit? So if it's like a very unbalanced kind of like simplification, like
oh, I see. So do you mean that, so if we take the mean and if we take the mean across all terms we produce, and one of those terms actually gets knocked out, we kind of miss
yeah.
that? Well, actually, that's actually a very good question. So one of the subtleties of reinforcement learning is that it's actually pretty difficult as a discipline, and a lot of the effort that goes into trying to develop these algorithms specific for different use cases is actually this choice of reward function. So we actually experimented with a few. One, for example, we just looked at trying to, instead of looking at alpha, we looked at like just removing as many T gates as possible. So just like total T count. And this was just, it's actually what you suggested is actually worth trying. We just found that we got the results we achieved and reported on using this alpha, and it seemed to do pretty well. But yeah, it's like we're still kind of pushing this project a bit further and developing it more. So actually, it might be quite cool to try and look at reward functions like the one you suggested and see what does better.
Yeah, I'm wondering like if you try to take into account the fact that it's an exponential process, like what is like exactly the reward that like actually captures the optimal sort of reward.
Yeah.
And then like a size point, like if you have like one of these diagrams and it's actually equal to the 0 diagram, then like the diagram might contain a lot of T gates, but actually it's like has a scalar 0, so you can just ignore it. Like, does this take that into account? Like it says, oh, actually, yes, this has been completely simplified, this diagram.
I think at the moment we just do this kind of naive reward calculation, but it'd be worth like trying to implement. The other thing is you can also look at other metrics like C0 count and all these sorts of things. So there's a lot we could do there. But this will become actually like kind of my last few slides will kind of talk a bit more on this sort of theme. Yeah.
Yeah. All right.
Okay.
Sorry, just to follow up on this reward function. So when you experiment with a different choice of reward function, did you get very distinct results, or they are all giving you similar results?
We found that with the first thing we tried, which was just reducing T count without looking at the efficiency coefficient, it didn't do as well. And this was the one we find it actually performed quite well. But we didn't actually explore mainly because we had a deadline to submit this to NeurIPS. We basically just kind of thought about the most systematic way to do this. We thought effective alpha is kind of nice, simple. It makes sense. There's like a logical argument towards using it, and it ended up performing well. So we stuck with this one. But yeah, with this, we're definitely looking to look at other metrics and see how that works. Okay, I'll move forward. And yeah, so just to summarize what we did there is that we placed the decisions which require a lot of time and domain expertise with AI-based decisions. And one thing I think is quite cool that will become relevant for other applications is that we're interleaving AI-based decisions with algebraic manipulations, which actually, these AI decisions are somewhat probabilistic, and we interleave them with these deterministic algebraic manipulations, which I think is quite nice because it means that there is this kind of synergy between this AI, training these AI agents and the use of the ZX calculus. That neither of these methods would have been as effective just in isolation. So combining them is quite nice. Okay, there's here's ingredient 2, which are these GNNs or graph neural networks, and these are effectively neural networks that perform very well on graph structured data. And so you can imagine these are quite useful and have proven useful in things like antibiotic discovery, where you can represent chemical molecules and different things as graphs. Traffic prediction as well, where you represent a roadmap as a graph. And fake news detection and other sort of social network sort of applications where you can represent a social network as a graph. So the idea is that graph neural networks perform very well when you have something that you can represent as a graph. Now, that looks quite nice for ZX diagrams, which have a graph data structure. And so we can, this is where ZX becomes kind of pretty important, is that it allows us to represent quantum circuits as graphs. And even better, we can get this sort of minimal graph representation using a graph like normal form, where we just reduce all the spiders to Z spiders and all the non-boundary edges to Hadamard edges. And what we can see here in this diagram is that what the graph neural network really takes as input is we ascribe some kind of like data embedding, which ends up becoming the internal representation for the neural network of the node as these sort of vertex embeddings. And we also feed it the edge connectivity. So it basically looks at all the nodes, and it has some awareness of how all the nodes are connected together. And in the processing, it starts from just knowing the initial information is just what's the phase on the node. And as it does some internal processing, it builds some kind of internal representation of these nodes that takes into account all the surrounding nodes. And this is facilitated by the edge connectivity. So the short version of this is that when we represent ZX diagrams in this way, they're just naturally amenable to these graph neural networks. And so using these two ingredients of reinforcement learning and the graph neural networks, we train a graph neural network-based agent using a reinforcement learning algorithm called proximal policy optimization. And so what the network does is that at each point, at each point in the sort of the steps of this algorithm, it chooses a vertex to apply a cat decomposition. And if no cat decompositions are available, it applies a magic 5 to a choice of 5 vertices instead. The architecture of our model kind of looks a bit like this. So in this middle diagram where we have a ZX diagram that gets fed in. And then we have this kind of this base neural network that looks at the ZX diagram and sort of extracts the features. That's the internal processing I was talking about previously. So it kind of thinks about the ZX diagram, and then based on what's available, it either chooses somewhere to perform a cat decomposition, or if not available, it performs some kind of magic 5 decomposition. So it's kind of got this like base internal processing, this base sort of brain, if we want to call it that just thinks about the ZX diagram generally in the context of decompositions. And then it has specific kind of pieces that either look at what's the best way to apply a cat decomposition or what's the best way to apply a magic 5. Now, one thing I should highlight here is that it doesn't prioritize any of the cat decompositions in order of efficiency. It's now given free rein as to which of the 4 cat decompositions it could apply, and then picks based on that. And with the Magic 5 decomposition, what the deterministic algorithm does, the one I mentioned previously, it doesn't have a preference to the vertices. It picks randomly. Whereas now what our neural network does is it actually does choose which vertices to decompose. It will actually try and, well, the aim is that it will learn to pick more fruitful Magic 5 decompositions when it actually picks them. And so in a sort of more AI lingo, we have turned this decomposition selection problem into what we call a node classification on graphs problem. And we train it using reinforcement learning. And as I mentioned before, the nice thing is that we're now getting this synergy between like the ZX calculus and an AI agent that is using it as part of a pipeline. Okay, so now the results. And we trained and tested on 3 different classes of diagram. So we did some Clifford T circuits. We did some grids. We basically produced grids of spiders, and we did random graphs, which were generated using the Erdős-Rényi model. And then we compared the results to the existing algorithm. And these are a summary of the results we got, where we improved the Magic 5, which you might expect because we're basically going against random choice, did significantly better. And another thing is that when we actually did the cat decomposition as well, we outperformed the existing state-of-the-art, and we got a lower spread as well, so more sort of predictable results. The graph on the right is quite nice as well. And so what we find is that our method also exhibits better scaling behavior. So actually, as we increase the number of T spiders that we actually have to remove in the diagram, our model, the number of terms we end up with, in other words, how efficient our overall decomposition is, actually scales a bit better. The number of terms increases more slowly. And some intuition to why this might be the case is because, as I mentioned, what our graph neural network is doing to some extent is it's actually taking into account the broader diagram context when it makes this choice of decomposition. And so that allows it to kind of to work with bigger scale diagrams. And yeah, just as a sort of idea that, the number of terms we end up with is really what gives us the cost of the classical simulation, or as a proxy for it at least, because there's obviously the inference time of the model versus like the computation time of the decompositions for non-AI methods. But if we look at just the number of classical terms to simulate, we find that we get a significant improvement if we just take the mean across the benchmark, which I should note is actually quite a wide range of circuits. So this kind of this is kind of quite a high level sort of estimate. Okay, so to summarize, we trained an AI agent to more efficiently simulate quantum circuits, and our approach was combining AI-based decision makings with the algebraic manipulations of the ZX calculus. We outperformed state-of-the-art on some initial benchmarks of different types of circuits. And one cool thing is that performing this task by hand requires a lot of time and domain expertise. So what that basically means is that good decisions about where to apply these decompositions can be pretty counterintuitive and not always obvious. And while a human expert requires often years of training to actually get to the point of manipulating diagrams of ZX effectively, we can train an AI model in just a matter of days or hours. So that sounds like absolute doom for any ZX researchers. They're like, oh no, even the AIs even come for us. But actually, I'm going to argue that that's not the case a bit later. So just as a brief discussion about future directions, we could train a benchmark against a broader class of circuits, benchmark it against other metrics, and benchmark against other methods like tensor networks, for example. And then there's lots of stuff we could do on the AI side, like try different reinforcement learning algorithms, different architectures, transformers being the very mainstream one. There's also the reward function we were talking about earlier. And also, we could try and address these more tasks using the same kind of paradigm. So, as I was saying, this whole thing is actually very good for ZX researchers. What our work kind of suggests is that we have a few ideas for applying AI to quantum computing using frameworks such as ZX calculus. We have a way of representing quantum circuits using ZX that is agnostic to the qubits and the gates, where we can just reduce a circuit to this graph-like normal form and feed it into a graph neural network. And there are actually a multitude of other tasks in quantum computing, like circuit routing, optimization, circuit synthesis, where actually the best known results come from heuristics and human experts. And a lot of these tasks take this kind of format where we have some sort of agent performing actions in some kind of environment. Now, the idea was that you have initially these heuristic methods take either a heuristic algorithm or a human expert as the agent performing these actions to perform some kind of task. And what we can do instead is we can train an AI to do it for us. Now, what I think is good for us ZX researchers is actually it isn't quite as simple as we just throw AI at it and it works. The real challenge in trying to perform these tasks or tackle these problems using ZX and AI is that actually it's not always easy to formulate these quantum computing problems or these ZX tasks in a way that we can integrate into an AI framework that actually trains and outperforms what we can do already without AI. So the real kind of fun research problem is, we've got someone who fully understands ZX, and they want to try and put what they're trying to do in ZX into a sort of format that we can quite easily formulate as an AI problem that can be trained. And so my feeling is that ZX is actually perfect for this. So yeah, on that optimistic note, I'd like to thank you all for listening.
All right. Thank you very much, Alex. If people want to clap, they can use the little clapping emoji thing in Zoom. All right. I see we got a question in the chat, which I'll ask for this Otto John. He asks, what data set are you using?
Oh, okay. So yeah, let's go back to these bits. Yeah. So there are some numbers I haven't got them on off the top of my head, but we decided on Clifford T circuits, grids, and random graphs. And what we did is we generated these using physics, and we made them sufficiently. We effectively tried to make them sufficiently hard that they were both kind of like a challenge for the existing method and the AI model. And so in the reinforcement learning process, we actually generate all three types of circuits on the fly. So we'd have our reinforcement learning setup, and what the AI would be trained on is just these randomly generated circuits. And we'd continually do that until we achieve some kind of performance. Then what we do is we have So the data set for training the AI is randomly generated samples from these three types of circuits. Now, the evaluation data set that we actually compared these two things for, these were a fixed data set that we used at the end. So we kind of took those and we compared these to the fixed data set that we did, once again generated randomly, but we did keep. Yeah.
All right. I have a ton of questions, but I'll let the other people ask questions first. Sarah?
Thank you for the talk. I also have a question about this slide. Firstly, you said that your method is showing more scalability than the state of the art. And when you talk about scalability, do you mean the number of qubits or do you mean the T count?
We mean the T count. So what full reduce does is it kind of what really acts as a barrier to this full reduce algorithm is the T count, really. So the T phases. And so yeah, it's the T count really that we're interested in. That's like our non-stabilizer bit. So yeah, it's a T count scaling.
And is it possible to find a lower bound for the second graph? Like, because if you're always comparing yourself to the state of the art, you can never know for sure whether this method has achieved the optimal solution. Or like finding a lower bound of the stabilizer terms, the number of stabilizer terms is NP hard or like some other, like, complexity class that you can never know.
That would be good to look at, actually. I'm not aware of any lower bounds on how this would scale, actually. But yeah.
Thanks.
Okay. Do you have any other questions in the audience? I see one in the chat. How do you get from the classification to the policy? So what are the classes that you classify nodes in? From
Oh, okay. I see. I think I know what this is asking about. So so what we have is we have these two. Our model is basically something that has two, or the output of a model is one of these two heads. And so what this does is this when the ZX diagram is fed through the model, what comes out at the other end actually preserves the graph structure. So you get an output for each spider in the diagram, and those output and what we get is a probability distribution over each spider. And so that's kind of our policy is going to be the probability. Well, yeah, the policy is going to be the probability distribution over each spider. And so what happens is that, typically what our model will say is that like these are this is the most likely spider to be a good one to pick. And one thing to note is that at training time, just so we get some kind of, there's an exploration and exploitation kind of trade-off we get. So, once you've actually trained the model, you kind of think, okay, well, the probabilities don't matter. We want to pick the one with the highest probability usually. However, that's not good for training because the model doesn't explore all the possibilities we like. So we have this probability distribution that we kind of sample from over all the spiders in the graph, and that's what we call our policy.
But in the policy, you don't need a single point, but in Magic 5, for example, 5 points. How does this work? So which five,
yeah. Okay. Yeah, actually, that's a very good question because this took a while for us to kind of get to work when we were doing this. So yeah, so basically the naive way to do this is like you have in reinforcement learning, just for everyone else's context, you have like an action space. So like the number of this is kind of like all the possible actions you could take in your environment. And so for just picking one vertex in the ZX diagram, that's okay. That scales the size of your action space scales with the number of vertices you have. For the Magic 5, where you have to pick five spiders, it becomes a bit more complicated because that scales with, let's see, so you have number of, yeah, that scales, so you have, you pick one spider from the diagram, and then, so that gives you like, let's say there's n vertices in the diagram, that's like n possible choices. But then you have to pick another spider, so that gives you n times n minus 1 possible choices. So as you can see, like what happens is that you kind of have n times n minus 1 times n minus 2, and suddenly you've got, if you're thinking about like all the choices as all the possible 5 vertices you could pick, you've suddenly got something that scales with like n to the 5 in the number of vertices. So for us, that actually became intractable. Like it was, we would have to have a model output that would be like quite quickly generating, having to pick from like millions of different possibilities. So what we do instead is that we have a single probability distribution, and we thought, okay, well, it's not like it wasn't this doesn't quite make sense like from a theoretical perspective, but it's the best we can do. And we use that, and what we do is we sample from this probability distribution to get the first spider. We then zero out the probability for that spider, and then sample from this new distribution where we can't pick spiders that we've already chosen. And we thought, oh, this is never going to work. But actually, it ended up working, as we saw in the results. And so I guess to some extent, although it's not theoretically, it might not be optimal, the model does somehow manage to learn probability distributions that work quite well. And it might also be the case that, it's not necessarily the combination of 5 spiders you pick, but it's more each individual spider that you pick for this Magic 5 is kind of good to remove. So yeah, it's a very good question because it was quite an interesting challenge to try and overcome when we were doing this research.
Sorry, how do you calculate the probability distribution of each vertex?
So it's the model itself that calculates the probability distribution for us, and that's what it's trying to learn basically. It looks at a graph, and then it says, okay, here's a probability distribution over all the nodes, and I'm going to try and increase the probabilities for the ones that I think are the best places to do a decomposition. And for the Magic 5, what we do is we then take that output probability distribution, and because we have to pick 5 vertices without replacement, we start with this distribution from the model. We pick a vertex, and then for the next vertex, we use the same distribution, except we zero out the probability for the spider we already picked, and then renormalize the distribution and sample from that until we have 5 vertices, basically.
Thank you.
So I have a bunch of questions. Some about like the data you collect and some of like the methods you use. So I'll ask those first. So if I understand correctly, you're doing reinforcement learning, like the entire game you're learning on is a single step, right? Like it only sort of asks you like, pick me the best vertex that I will do the rewrite on. You're not training on the entire sequence of you do this decomposition and you get like different diagrams and then you do decomposition there. Like you don't do sort of end-to-end learning. You train on a single step in the decomposition process.
Well, actually, that's the way it works is actually pretty cool. So I think the state of the art that we use, proximal policy optimization, and most reinforcement learning algorithms now, what you do in the training process is that you have a kind of episode, as we call it, which is, for us, in our case, you start off with a diagram you want to decompose, and the episode is that entire end-to-end process of decomposing the single diagram into all the stabilizer terms. And what happens is that The training process kind of acts in this kind of cyclical process where we perform an episode. So the model is not training. It just takes what it does. It takes its current like state or current policy, as we call it, and carries out an episode. It says like, okay, here's the diagram, decompose it as best you can. And it collects an experience of that episode. So it collects all the observations it's made, all the rewards it received in this entire end-to-end process. It's only then that actually you do that for a few episodes, so you get like a batch of attempts, and then it takes all this data, this end-to-end process, and then goes through a training, and then actually tries to update its policy and try and improve based on these end-to-end experiences. And what the training process does is it doesn't just take into account each step in each episode. It actually looks at the reward it got for each step, but also like in a sort of discounted way, all the rewards it received in the future. So it associate with each action that it makes. It doesn't just associate the immediate reward. It also associates all the rewards it got down the line. So it does in fact like kind of train on the whole end-to-end process, which I think is one of the things that makes it so powerful.
Right, because that would be my follow-up question. Like, what if you combine this with like a AlphaZero style stochastic tree pruning, like kind of thing. What was the name again?
Monte Carlo tree search.
Monte Carlo tree search, yeah, exactly.
Yeah.
Like, I was wondering like how that relates, like if that would be like a useful thing to sort of put on top of this, or if that's not necessary because of the thing you just described.
I think it would be a good thing to try. The nice thing is that most reinforcement learning now does already take into account like future rewards it received after. Now, the AlphaZero style approach is actually pretty powerful. I think there was a paper. I know there was a paper on using Alpha Tensor. This wasn't ZX actually, but it was using Alpha Tensor to perform, I think, optimization. So there's definitely people thinking about.
Yeah, I was on that paper.
Oh, you were? Okay, yeah. I was thinking there's a few names that I can't recall off my top of my head that I knew. Yeah, so yeah, indeed, like there is I think there's a lot of promise for using that kind of approach, especially like not just this, but also like on the optimization front and for a load of other tasks.
Yeah.
And yeah, I think that would be quite like I think the main barrier is the computation cost. Like these things, these simulations of compute.
So is the inference that should not be that expensive, right? Because I'm assuming this graph neural network is not that big, or am I mistaken about that?
Yeah, the inference is pretty good. It's most of the time and most of the compute comes in the training process. And it's the same with the AlphaZero approach. It's really the training and all these simulations and like collecting these experiences and learning on them.
But then
afterwards,
now that you've trained it, you could in principle just put this Monte Carlo tree search on top of that, right? You just like you just ask the neural network like, give me a couple of good nodes, and you explore a bunch of them, and you go to a certain depth, and you keep the best ones, and that's sort of like independent of like what you've trained now. I would guess. But,
yeah, that might work. I wonder whether it would work because I haven't really experimented much with the Monte Carlo tree search stuff yet. But I don't know whether one initial thought is that it might be a really good shortcut if let's say you have limited resources to do this kind of huge distributed training process that like Google do. One reason it might not work is that these agents are often very sensitive to the scenario you train them in. So if it wasn't trained in a Monte Carlo kind of tree search sort of environment, it might not thrive as well as like one that would, is my expectation.
That would also be like a question I wanted to ask. With graph neural networks, they essentially act on local information in the graph, right? So it has the generalizability to larger graphs baked in. Or am I mistaken about sort of graph neural networks?
So what they do is they have this thing that we call message passing. So each node, each node kind of has its connectivity to all its neighbors, and so you have a bunch of layers basically, and for every layer you have, the node aggregates information from its neighbors. And what that means is that if you think about the messages being passed between nodes, you can, just with one layer, a node can gather information about all its distance 1 neighbors. But if you then introduce a second layer, you've got information that comes in from all the distance 2 neighbors to all the distance 1 neighbors. And those distance 1 neighbors can now pass the collective information of, distance 2 nodes and the distance 1 nodes to a node. So like the more layers you have, the more reach you get. There are other ways, there's ways in the research that try to get around this by like having kind of distance passing messages kind of across larger distances in fewer layers. But yeah, there are actually a lot of limitations to graph neural networks, theoretical at least. I don't know the specifics, but there's things like not being able to discern between isomorphic graphs and things like that, which is something to keep into account. But that's also why I think, like I mentioned, transformers and other architectures, because transformers just seem to do well on everything, and no one understands why. And so maybe that's just like one way to try and get around this. By feeding some ZX representation into them.
So maybe related to scalability, with small enough graphs, you can just exhaustively determine the best possible set of decompositions. Do you know whether your method gets the optimal one in like those small cases?
We haven't actually looked at that. One thing that I think I kind of want to do quite soon is like, which I haven't done yet, is just set up some code to just take examples of diagrams and see what decisions the model is making just step by step. If anything, just for kind of like an intuition. And another thing is to actually see if it does anything counterintuitive to what we might expect as well.
Yeah, because that was also something I was wondering, because you could imagine certain simple heuristics you do to pick vertices. Because like now you've compared against our method, which is essentially picking random vertices, right? So it's not using any information on the graph, but you could imagine trying 10 different ones and picking the best one, like having some like fixed set of random choices you make, and you just pick the best one from there, and like probably you will get an improvement if you do that. You could imagine like picking like a dense set of vertices or a very sparse set of vertices that are very far apart in the graph. Just trying like a whole bunch of very simple heuristics that might be better than the random choice we make, and then seeing if your method still performs better than like those random choices. I would assume so, but it would be good to see like how much of the effect is just using like a simple heuristic on top of like our very, very stupid choice. And how much
that'd be very good to see. It'd be like at the moment this is the only comparison we've made, which is it's the kind of like the deterministic choice of decomposition, but or as you mentioned, a random choice of vertex. It'd be quite good for just trying to push like the boundary of like, okay, what do we have to beat? Because there's definitely a lot more I think can be done with this kind of training this model.
Yeah. Can you go back to the previous slide? Because like here with like you have like on the left plot the two things on the right, like your method versus our methods, like they seem to be like almost indistinguishable in terms of like the data there. So
yeah, they're pretty close. So what these box and whisker plots are is they show the median as well. So I guess they're looking. I haven't got the numbers available, but there's also I think a distinction in the mean. But yeah, they are actually pretty close. So I wonder whether like if you start to add a few more heuristics to the deterministic method, whether it might start like out competing with our model.
Yeah, because like you on the right you have the scaling, but then I'm not sure how many data points each of these crosses and circles is. Like there are these statistical methods to determine whether like a difference into lines like this is statistically significant based on number of data points and stuff like that. So I'm wondering whether this is like a real effect that you're seeing, this like better scalability.
Oh yeah, okay. Yeah, we should actually look at that.
Yeah. If each of these data points is like a lot of circuits, then probably it is significant. Yeah.
Yeah, it's quite a few, but we don't have metrics on whether it is statistically significant, but that's actually a very good thing to look at. Yeah.
There was a question from Otto John in the chat. He asks like why the number 5 for the magic 5 decomposition? I want to and why not other values? And yeah, so that's the question.
Okay. I think it's to do with the theoretical derivation that's in the paper listed on this slide actually. I think we chose it mostly because then we had a comparison with something that was with existing results. But I think there is I know you can derive it from it's kind of based on one of the cat decompositions, but more general. I don't know much more than that aside from its yeah.
Yeah, I would guess that going higher than 5 is difficult, but you could in principle do like a magic 4 or magic 3 decomposition. So it's like right now you have like 2 policy heads, and you could in principle add a policy head for magic 4 and magic 3, and like maybe it tells you actually in this case you should do a magic 4 instead of a magic 5. That's
Yeah, that's actually one of the things we want to look at as well, is like just giving the model like a whole arsenal of different decompositions that we can find, and just like let it go ham and just try whatever it can to try and do the best decomposition. I guess the difficulty there is like we want to try and like not just how. So at the moment we have a specific ordering, so we like try the cats first, we try the magic 5 next. But it'd be quite cool to have like a bunch of decompositions we can do, and then also have the model pick from all the decompositions. So it might think, actually, you know what? Even like a magic 5 might actually be better than a cat here, and then decide to do a magic 5. But it's quite technically difficult, or like in practice, it's not immediately obvious how to do that well.
Yeah. He also asks, when you say cat decomposition, do you mean KEK decomposition? K-E-K? K-E-K? I'm not sure what that is. But,
No, I haven't heard of the cat decomposition. But yeah, the cat. Let's see. Here's cat 4. No, we mean any of the cat cat 3, 4, 5, and 6 decompositions. And basically, what they do is they take these magic states, like you see on the left, with either like with 3 to 6 spiders, and decompose them based on a formula. And they produce either 2 or 3 terms, basically.
yeah. So maybe I should say to John is that this is called a cat decomposition because the state on the left here is called a cat state. So it's a decomposition of a cat state. I think the KEK decomposition you're talking about is a way to decompose a symplectic matrix, which is not a relevant concept in this setting.
Okay. Yeah, the magic and the cat decompositions are quite good choices because we allowed us to call our model the magic cat model, which we were very happy about. And Matthew and Richie and I.
Very good. All right. Are there any other questions in the audience?
It's a very basic one. So when you talk about the cat hat and like the magic 5 hat, what do you mean by this hat?
It's usually just it's not so much a strict technical definition, but usually you just use head to refer to the output of your model. So like the idea is that when you're thinking about designing neural network architectures, oftentimes you have this big kind of like combination of different things. So it might be that you have part of your network, part of your big network is made up of like some graph neural network or some like just straightforward like fully connected network. And the way you piece all these components together, it might be that you want to, I guess it's quite hard to like actually quantify this, but you might want to think of different parts of the network as performing different tasks. So the head is basically the part that produces some kind of output. And so we call it the cat head because it produces the output for the choice of cat decomposition, whereas the magic 5 produces the output for the magic 5 decomposition. And then the features extractor is the one we think of as like just extracting kind of important features about the ZX diagram, which it then feeds to the output heads.
Sorry, can I understand that the feature extractor is how you, as a person who define the reinforcement learning to the side? So if you choose different feature extractor, then you'll have different cat head and magic 5 head?
So I guess if you the way the kind of the network's all trained in one go. So I think if I'm understanding correctly, what happens is that the cat head and the magic 5 head will get trained with the features extractor. So all the kind of stuff that gets learned will kind of happen in this kind of synchronized way. So if you swapped out for a different features extractor, which we haven't tried, but I would guess that like if you it might the new features extractor would probably have been trained in a different kind of stochastic way with different heads. So it probably won't feed very useful information into the heads. So yeah, the whole thing acts as one kind of unit.